All right, welcome to chapter 4. Today we're going to talk about transformations of graphs and symmetry. So transformations are when you shift a graph left, right, up, down, stretch, compress, etc. So we'll talk about all those kinds of things. So here's a quick example. Shifts of a function. So graph these two functions. We'll do this together in just a second. On the same set of axes, and let's see what happens when we do this, right? So we notice they're both essentially the same function, x squared, which is a parabola, right? But then this one right here, we're adding to that function 2 units. So let's see what happens when we do that. All right, so we'll start with this one. So we're going to plug in some values right here. All right, so we plug in each of these x values into f of x, which is x squared. So we're going to square each value and see what happens. All right, so negative 2 squared is positive 4. So that's actually something we want to talk about here real quick. Be careful. All right, so negative 4 in parentheses, I'm sorry, negative 2 in parentheses squared equals positive 4, right? But be careful, if you have negative 2 squared like this, remember that PEMDAS takes over here. Okay, so PEMDAS says do exponents first, right? We do exponents first, which means we're going to take 2 to the second power, which is 4. Then we multiply by the negative 1, which is negative 4. Okay, so this is important. Be careful when you have algebraic steps like that. Okay, so we'll continue on here. Let's see, we're going to plug in a negative 1 into the function x squared. So again, same thing, negative 1 times negative 1 is positive 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. Okay, so we did that. Now let's do the same x values. We're going to plug these same x values into the g of x function up here. So we're going to square each value, then add 2. So what we can actually look at is we can look at these values of f of x and just simply add 2. Okay? And that's what we're going to do. So let's add 2 to each of these f of x values. So we'll get a 6, a 3, a 2, a 3, and a 6. All right, and then we're going to graph these. So we'll graph f of x using the same color, the pink color here. So we have 0, 0, 1, 1, negative 1, 1, and 2, 4, and negative 2, 4. And then we graph this, right? So we'll make a little curvy line here with some arrows on it. Make sure the line has some curve to it. It's a parabola, okay? All right, so that's x squared. That's the f of x function there. Now let's graph g of x. All right, so let's look at these values. In the center, we have 0, 2. All right, and then we have negative 1, 3, positive 1, 3, negative 2, 6, which is up here, and positive 2, 6. All right, so we draw that parabola in there, and we notice what happens, right? We see that this part here moved up by 2, right? Moved up 2 units. So we can check it point by point. That point moved up 2 units. That point moved up 2 units. That point moved up 2 units. Every point on this graph we can see moved up 2 units, okay? So what that tells us is when we take a function, in this case x squared, and add 2 to it, we're moving in the upward direction, okay? All right, so then that's what we're saying right here. All right, so we notice the difference is from f of x to g of x. By adding 2 to the function, to f of x, we're moving the graph up 2 units. Okay? All right, and that's what we're going to tell you right here. So if k is a positive real number, just k is just some number, positive real number, the graph of g of x equals f of x plus k, right? So in other words, if we're adding to the original function, we will shift up to the k units, however many that number is. If we subtract k from the function, we move downward on the graph, that many units. Okay, so very, very important to remember here. All right. Okay, so let's try this again, but we're going to make it a little bit different here. All right, so we're starting with f of x equals x squared again. So we already know those numbers, right? So we can plug those in. Again, we're just squaring each of these individual x values. So we get 4, 1, 0, 1, 4. But now we got to be careful, right? For g of x, we have to follow PEMDAS. Okay, so I'm actually going to write a few of these out. So let's do -2 plugged into the g function. In other words, we're going to do g of -2. So what that means, replace x with a -2. Okay, but we have to do PEMDAS, right? So PEMDAS says do parentheses first, then exponents. Okay, that's very important. So -2 plus 2 is 0, right? And I'm going to write it out. You don't have to write this out. But so inside the parentheses is 0 squared, which of course we know is 0, right? Okay, so that's a 0. And we'll keep doing this, right? So let's do one more just for practice. So we'll plug in, so we're going to do a -1 now, g of -1, so it's -1 plus 2, quantity squared. So inside the parentheses, that's a 1 squared, which is 1. Okay, and we keep repeating that process. Plug in a 0, do the parentheses first, then square, we get 4, and we keep doing that. We should get 9 and 16. Now I know these numbers go off the graph. That's okay. It's just to illustrate what happens here. Okay, so let's graph x squared again. We did that one in the previous example, but I'm going to graph it again for you. There we go. And again, make sure these lines are curved. They don't have to be perfect. Well, in this class, of course, the online class, you'll be doing your graphs online anyway, so that shouldn't be too much of a problem. The computer program should allow you to graph it properly. All right, now g of x. Now some of these points are off the graph, but I'm going to show you what happens. So let's see, we're going to do -2, 0, -1, 1, 0, 4. And what I should have done was some values off in this direction here, right? But we can plug those in. Let's see, if we plug in a -3, we should get a +1. And if we plug in a -4, we should get a +4. Okay, trust me on those. Plug them in, you will see. And if we graph this, we now have g of x, this green graph here. And what we notice is just like before, well, not just like before, but similar to before. In the first example, we added 2 to the function and we moved upwards. This time, notice we're adding 2 to the x, right? When we add 2 to the x, this is the weird thing about adding and subtracting to the x, we move in the opposite direction. In other words, +2 means move 2 units in the left direction. That's very important. When we add to the x, we're moving left. When we subtract from x, we're moving right for our shifting. Okay, and again, just like we did before, we can notice every point has moved to the left by 2 units. Okay? All right, so make sure you understand that, and here we go. The graph of g of x is the graph of f of x shifted 2 units left. All right, again, very important here that you know this information, right? So if we're subtracting from x, that's what this notation means. If we're subtracting from x, then we move to the right h units. Okay, so opposite, subtract, move right, add, move left. Okay, very important. Okay, so these are just some different graphs at the bottom here. Now these are stretching and compressing the graphs, right? So we notice what happens if we just, well, we know this graph, right? X squared, just the plain old parabola, right? But what happens if we multiply that parabola by a whole number greater than 1? Notice what happens. Look how kind of wide this one is here and how thin this one is here. You guys see the difference? Okay, so that's a compression. All right, and then notice what happens here. So it kind of, well, let me talk about this one here, and then I'll tell you what's going on. Now we're multiplying by a fraction smaller than 1, right? Fraction smaller than 1. Actually, we notice it makes the parabola wider. Okay, so again, it's kind of that opposite to your thinking. If we multiply by a number, we make the graph thinner. A number greater than 1. If we multiply by a fraction less than 1, we make the graph wider. So very important. That's what they're telling you here. So stretching and compressing, I know the terminology here is a little bit rough, kind of a pain to understand. Go with what I said right up here. Okay, again, multiplying by a number bigger than 1, we compress it, we make it thinner. Multiplying by a fraction smaller than 1, we make the graph wider. Okay, very important. We also have reflections, right? So think of reflections just like a mirror, right? You look at your reflection in the mirror, it's completely opposite, right? So what they're telling you here is if we take any function and multiply the whole function by a -1, we're going to flip it across the x-axis. Okay, and I'm going to show you an example in just a minute. If we multiply the x by a -1, okay, then we're flipping across the y-axis. A way to think about this one here, because f of x is also known as y, right? So let me write this up here. This is also, actually it says it right there, right? This is also y. If we take all the y values, right, any values above the x-axis that are positive, if we multiply them by a -1, they're now going to be down here, right? They're going to be negative y values. Okay? So that's a way to remember that. And then right here, if we're multiplying the x values by a negative, that means any positive x values here now become negative x values. So we're flipping across the y-axis. Okay? So these are just some easier ways to remember this. All right. So let's actually see this happen now. So notice the only difference is we have x squared here and negative x squared. So remember, like I said before, what this is saying is really we're taking negative of f of x. Okay? We would square the numbers, then multiply by -1. All right, so we've done this one before. So the f of x, we know these numbers already, 4, 1, 0, 1, 4. But now it's actually the same, right? Again, we're just saying we're taking x squared and multiplying by a -1. Okay, so pretty easy, right? Take all these f of x values and just multiply by -1. And there we go. Okay, then we graph. So we've graphed a regular x squared parabola several times now. So we know what that looks like. I know mine's a little bit off, but do your best when you draw these out. And g of x is actually, you'll see it's just the flip over the x-axis, right? So still 0, 0, here, here, there, and there. So we notice right there, it's just like the x-axis. Think of the x-axis here as a mirror, right? The pink one's on one side of the mirror, green one's on the other side of the mirror. Okay? All right. So that's what we've got here. What do we notice between the two graphs? G of x is the graph of f of x reflected across the x-axis. Again, it just looks like it went through the mirror, right? Okay. Next thing we have is symmetry with respect to the y-axis. So symmetry, if things are symmetric, means you can, kind of cut them in half and you'll have mirror image on each side, right? Something to that effect. So let's see, the graph of y equals f of x is symmetric with respect to the y-axis. If for every point x comma y on the graph, the point negative x comma y is also on the graph. In other words, f of negative x equals f of x for all x in the domain of f, this is called an even function. Okay, and we're going to do some examples of that in a minute. Next one is symmetry with respect to the origin. Right, so the graph of y equals f of x is symmetric with respect to the origin if for every point x comma y, the point negative x negative y is also on the graph. In other words, if you plug in a negative x, you should get a negative of the entire original function, and if you get that, that's called an odd function. So these two things are important to know. Symmetry with respect to the x-axis. Right, this is also important to know. Just the other way around, right? If we're symmetric to the y-axis, we change the sign of the x's. If we're symmetric to the x-axis, notice we change the sign of the y values only. Okay? Those are important. Make sure you read over those a few times and understand it. Okay. So let's do a few of these things here. So, symmetric about the x-axis. So here's our function right here. So symmetric about the x-axis, right? We would have to have all the y values flipping over, right? And we can actually see from this graph here, right, that that's not going to be the case. If the x-axis is a mirror, there are no function values below there, okay? So this one is definitely not symmetric about the x-axis. About the origin, right? So we'll use this test right here. We're going to plug in a negative x, and we're going to see what happens, okay? All right, so let's see. F of negative x equals. So this is a test, right? So that means we're going to replace every x with a negative x. We've got to be careful when we do that. So we're going to say 2 times, and notice how I'm using parentheses appropriately here. 2 times parentheses negative x squared over negative x in parentheses squared plus 1. So then we use PEMDAS and we simplify, right? We talked about this one before. If the negative is inside the parentheses, it means we square the negative. In other words, negative times negative, which is a positive. So it's 2x squared, same thing in the denominator there, x squared plus 1. All right, so notice what happened. We plugged a negative x in for every single x and then simplified, but we got the exact original function back. No signs changed, nothing else changed. So look up here. That is the situation where we are symmetric with respect to the y-axis. We plugged in a negative x and we got the original function back. Okay? So what that means is we are, I should have left some more room here, my apologies. But we can just make this work. We'll move it down here. There we go. So, whoops. Not symmetric about the origin, but by the test we did here, yes, symmetric about the y-axis, and we can see that in the graph here, right? If the y-axis was a mirror, we can definitely see this graph is the same on both sides of the mirror. Okay? All right, so make sure you know these three little checks right here for symmetry about the different origin, or different areas, the x-axis, the y-axis, and the origin. Okay? All right, so let's see. On to section 4.2, combining functions and composite functions. All right, so these are a bunch of rules that you're going to want to make sure you understand. And you've probably seen these before. They shouldn't be that difficult, but we'll still talk about them. Okay, so the sum, right? So in other words, if we take two functions, f and g, right? Doesn't matter what they are. We'll go through some examples in a second, but any two functions, f and g, if you see this notation, f plus g of x, so this is how you say this, it's f plus g of x. This is not multiplication here, okay? It's important to know we're not multiplying in here. Okay, this is function notation. Those of you going on to calculus, business calculus, etc., make sure you understand your function notation very well. But the way we say this is f plus g of x. Okay? And what that means is we simply take the f function and add the g function. That's it. Nice and easy. Okay. For difference, difference means subtract. So f minus g of x means take the f function and subtract the g function. But be careful when you're subtracting the g function. We'll do an example in a minute. Watch out for parentheses. Okay. All right, next one is product. Product means multiplication. So f times g of x simply means multiply f of x times g of x. Nice and easy. Quotient means division, right? So f divided by g of x means we take f of x and divide by g of x, but we have to make sure we're careful, right? Remember back when you took your high school algebra classes or any algebra classes you've taken, remember we're not allowed to have a 0 in the denominator. So if g of x equals 0, then you cannot divide. Okay? All right, and here's just some examples of what that looks like, but we're going to do a written example right here. Okay, so again, make sure you know those rules. They're actually all pretty easy. Just the quotient one, the division one's the one you got to watch out for. Make sure you don't have a 0 in your denominator. Okay, so here we go. If f of x is x cubed and g of x is x minus 9, find the following and their domains. Okay, all right, so let's do this one here. So f plus g of x, we just said means take f of x and add g of x. Okay, well, f of x is x cubed, g of x is x minus 9, and there we go. Remember, we cannot combine any like terms here. There are no like terms to combine. For like terms, we need the same variable and same exponent. Okay, so this is what's known as a polynomial, right? We talked about those before. Polynomials, the domain of any polynomial is all real numbers or from negative infinity to infinity. In other words, you're allowed to plug in any real number you want and you get a valid outcome. All right, that's important. All right, part B, we're now going to do f minus g of x. Again, notice how I'm saying it, f minus g of x. By the rules above, that means take f of x and subtract g of x. All right, so f of x is x cubed. Now be careful, like I said, with the subtraction ones. Minus g of x. Well, g of x is x minus 9. So notice how I put it in parentheses. We need to do that because, watch, x cubed, we need to distribute that negative, right? That negative 1. In other words, share the negative 1 with everything inside the parentheses. In other words, multiply, right? So it's going to be minus x plus 9, okay? But that is still a polynomial, which means the domain is still negative infinity to infinity. Okay, again, the domain of any polynomial is all real numbers or negative infinity to infinity. All right, next one here, this is f times g of x, which means take f of x and multiply by g of x. So that means we're going to take x cubed, and again, we have to use parentheses, times x minus 9. So again, we distribute, we share the x cubed by multiplication. So be careful. X cubed times x is x to the 4th minus 9x cubed. Again, this is still a polynomial. So the domain is still negative infinity to infinity. Okay. All right, and then the last one, f minus g, or I'm sorry, f divided by g of x. So f divided by g of x means f of x divided by g of x. All right, which means we have x cubed over x minus 9. Now we can't reduce that, so we're done with that. But again, it does say give the domain. So again, like we talked about, we're not allowed to have a 0 in the denominator. So the way we find out the domain of a fraction is we take the denominator, set it equal to 0, and solve for x. Okay, in this case, we add 9 to both sides, so x equals 9. So remember what we're actually saying is we're going to exclude 9. So the domain is negative infinity to 9, not included. Remember, these parentheses means not included, union with, that's a u, 9 to infinity. So what this notation means is you could plug in any number except 9. Okay? All right. Moving on. Here's an example, average cost. So Sunny's greenhouse produces roses, and their total cost for the production of X 100 roses is this cost function here. Form the average cost function. So this is not something you have to know, but the average cost function is the quotient means fraction, of the cost function and the identity function x. So in other words, we take cost and divide by x. That's it. Okay? All right, so the average is the cost function over the identity function. Well, c of x was given up here as 50x plus 500, and I of x, the identity function, is x. All right, and there we go. That's what they wanted. So if they want to know the average cost, they just basically take the cost divided by the number of items. That's it. Okay. Next thing is composite functions. So composite functions, watch the notation here. So this is f of g, right? So that open circle, so notice it's not a closed circle. If it's closed circle right there, that's multiplication. Open circle means compose the two functions, right? So we read this as f of g of x. Same thing here. This is f of g of x. Just two different ways to write the same thing. Okay? All right, so the domain of f of g of the composed function is the subset of the domain of g for which f of g is defined. The composite function g of f, so notice switching the order, is defined by g of f of x or g of f of x, same thing. And the domain of g of f is the subset of the domain of f for which g of f is defined. And I'm going to go over that in just a second here. All right, so a composite function machine can be thought of as a machine within a machine. A composite function machine in which the input is denoted by x, all right, so we're inputting an x here, inside the function g. The outside function is f. The composite function rule is defined by f of g. And the composite function output is, again, symbolized f of g of x. Okay? All right, so this is important right here. F of g and g of f are not necessarily equal, so don't assume that. Okay, always just go through the work. Okay, and we're actually going to see that in a minute here. Okay, so here's an example. Finding composite function outputs. So we have three functions here, f of x, g of x, and h of x. All right, and they want us to give the domain of each new function formed. So this one says find h of f of x, right? And again, this is just same notation, just a different way to write it, or different notation, but the same meaning. Okay, so we're going to go kind of backwards. What we're saying is take f of x and plug it into the h function wherever you see an x. So in other words, we're going to take f of x and we're going to plug it in wherever we see an x in the h function. All right, so h of f of x means we do 1 over 3x minus 1. Okay, we took the f function and plugged it into the h function. All right, we want to find the domain. Remember, again, find the domain of a fraction. We take the denominator. In this case, 3x minus 1, set it equal to 0. Solve for x. So we'll add 1 and divide by 3. Okay, and again, remember, this is the value that we're going to exclude. So our domain is from negative infinity to 1/3, but we're going to exclude it with parentheses, union with 1/3 to infinity. Okay, and again, this whole notation means all real numbers except for 1/3. Okay, so moving on here, f of g of x. So we're going to take the g function and plug it into f. Okay? So this is what we're going to do. So f of g of x, so that equals 3. So where the x is in the f function, we're going to replace it with the g function, okay, which is 4 minus x squared, and then minus 1 to finish off the f function. And we're going to distribute the 3. So that's 12 minus 3x squared minus 1. We can combine the 12 and the negative 1. They're like terms. So this gives us 11 minus 3x squared. Okay? Notice this is a polynomial. Specifically, it's a parabola. So any polynomial, again, the domain is from negative infinity to infinity. Okay? All right, moving on. Next one is g of f of x. So we take the f function and plug it into the g function. Okay, so g of f, of x equals, so we get 4 minus, instead of an x, we're going to put 3x minus 1 and square it, right? Plugging in the f function into the g function. We'll distribute the negative sign here. Okay, so we get, 4 minus 3x. Oh no, my mistake. We're not going to distribute. I messed up. Remember PEMDAS, right? So we have to do the squaring first. So we're going to FOIL. Remember FOIL first, outside, inside, last. So we're going to do 4 minus parentheses, because we're foiling inside the parentheses there. 9x squared minus 3x plus 1. Now we distribute the negative sign to everything inside here. So 4 minus 9x squared plus 3x minus 1. So we notice we have some like terms, right? 3x. There we go. We have the 3x's here, and then we have the numbers here with no variables. So we can combine those. So we will get, let's see, so we'll get negative 9x squared. 3x plus 3x is 6x. And 4 minus 1 is positive 3. So again, this is a polynomial. Again, it's a parabola. So the domain of all polynomials is negative infinity to infinity. All right. Okay, moving on. So section 4.3, we have one-to-one and inverse functions. So a function f, so one-to-one functions. A function f is a one-to-one function if each output, so each y value, of the function corresponds to exactly one input, an x value, in the domain of the function. This means there's a one-to-one correspondence between the elements of the domain and the range. Okay? All right. So, determine if each of the functions is a one-to-one function. In other words, we're going to plug in a positive 2 and a negative 2 and see if we get the same answer. I'll show you. Okay? So in this case, f of 2 means we're going to replace the x with a 2. And remember PEMDAS, do exponents first, then multiply by 5. Okay, so 2 to the 4th is 16. 5 times 16 is 80. Okay, so we just found f of 2, but now we're going to find f of negative 2. Okay, so what we have to see is, do we have, for multiple inputs, do we have the same output? If so, then it's not one-to-one. Okay, so let's see, f of negative 2 means 5 times negative 2 to the 4th. Again, the negative 2 is inside the parentheses, so we're going to take the negative to the 4th power. So remember, a negative to an even power is a positive value. So this will still be 5 times 16, which is 80. So again, for two different x values, two different inputs, we have the same output, same y values. So that means not 1 to 1. Okay? All right, so if you take two different inputs and get the same output, the function is not 1 to 1. All right, so part B, let's try it again. We're going to do the same thing, find f of 2. All right, so we'll plug in a 2. So it's 2 to the 5th minus 2. So 2 to the 5th is 32 minus 2, which is 30. Okay, and then we'll find f of negative 2. So careful, this is negative 2 to the 5th minus 2. Negative 2 to the 5th, so a negative to an odd power is negative. Okay, so we'll get negative 32 minus 2. Negative 32, subtract 2 more, we get negative 34. Okay, so that means, since we got two different values here, means this is a 1 to 1 function. Okay. All right. All right, so then we have inverse functions. So functions f and g, for which f of g of x equals x. In other words, if we take the g function, plug it into f, simplify, and we get a plain old x. And if we do the opposite, if we take the f function and plug it into the g function and get a plain x, if both of those are true, then we say we have these two functions are inverses of each other. Okay? So inverse functions, the functions f and g are inverse functions if, whenever the pair AB satisfies y equals f of x, the pair BA satisfies y equals g of x. In other words, we're flipping the domain and range, we're switching the x's and the y's. Okay, and like we just set up above, when this happens, f of g of x is going to equal x, and g of f of x is also going to equal x, for all x in the domain of g and f, respectively. The domain of the function f is the range of the inverse g, and the domain of g is the range of f. That's just fancy talk for, again, switch the domains and range. Switch the inputs and outputs, switch the x's and y's. Okay, all three of those statements mean the same thing. Okay, so here's an example, temperature conversion, right? The function that can be used to convert a temperature of x degrees Celsius to Fahrenheit temperature is this function here. And going back the other way from Fahrenheit back to Celsius, we would use this function here. So to see how the two conversion formulas for temperature are related, find f of g of x, find g of f of x, and let's see what happens. Okay? So f of g of x means, again, we're going to take the g function and plug it in for x in the f function. Okay, so that means we get 9/5. Instead of x, though, we're going to plug in g of x, which is 5x minus 160 over 9 plus 32. Okay, then we simplify. Notice we have 9 divided by 9. Those reduce away. Remember, not cancel. They reduce away. And so we'll have 5x minus 160 over 5 plus 32. Now, notice when we have subtraction or addition in the numerator, we have to treat this as two separate fractions here. Be careful with that, okay? So in other words, we're going to do 5x divided by 5, which is plain old x, minus 160 divided by 5, which is 32, okay? So be careful with that. So plus the 32 here, but negative 32 plus 32, so this equals x. That's good news, right? That's half of what we need to find. When this equals x and this equals x, then we know we have inverse functions. So we have to test it in the opposite direction. We now have to find g of f of x. So the same thing, we're going to take the f function and plug it into the g function wherever we see an x. So it works out this way. 9/5 x plus 32 minus 160 all over 9. Okay, so we're going to multiply this 5 into here, which means 5 over 5 reduces, right? So we're going to end up with 9x plus, and 32 divided by 9. Or no, I'm sorry, not dividing by 9. We're multiplying by 5, sorry. So plus 160, so 5 times 32 is 160, minus 160 all over 9, there we go. Well, 160 minus 160 is 0, so we get 9x over 9. 9 divided by 9 is 1, so we get an x. So there we go. F of g of x equals x, and g of f of x equals x. Therefore, f and g are inverses of each other. Okay? All right. Next thing we have is the horizontal line test. So this is an easier test for one-to-one. Function is one-to-one if no horizontal line can intersect the graph of the function in more than one point. Okay, so horizontal line test. Notice this one here, right? Here's our horizontal line. It clearly intersects this graph in two places, right? So this is not one-to-one. But notice in graph B here, it doesn't matter where we put a horizontal line, it's not going to hit the graph more than one time. Each individual horizontal line is not going to hit the graph more than once. So this, yes, this is one-to-one. Okay, so that's the test you want to make sure you really know, this horizontal line test. Okay? All right, finding the inverse of a function, this is important. All right, so this is the process. This is an important process, and it's written out here, but I'm going to show it to you. Okay, so first thing is we take f of x and we change it to y. That's step one. Okay, then what we're going to do is we're going to magically switch x and y, not through algebra, just magic, literally. So in other words, we're going to say this is now x equals 4y minus 3 over 5. And now we're going to solve for y. We're going to get y by itself. So first step is multiply both sides by 5, right? 5 over 5 reduces, so we get 5x equals 4y minus 3. We'll subtract 3. We'll add 3 to both sides, right? So we get 5x plus 3 equals 4y, right? Because negative 3 plus 3 would be 0. And then we're going to divide by 4. So we're going to say 5x plus 3 over 4 equals y. Now the final step, and this is very important, very, very important. It's not really y anymore, okay? It's kind of a fake y, right? So what we have to do is use proper notation. In other words, we're saying the inverse of the function, right? So that little negative 1 right there is not an exponent. It means the inverse of the function is 5x plus 3 over 4. Okay, and that's the proper way to write these out. All right. Okay. Let's see, graphs of inverse functions. So graphs of inverse functions are symmetric about the line y equals x. So this 45-degree line. Okay. Let's see, example. Here's an example for an investment. Business property is purchased with a promise to pay off $60,000 loan plus $16,500 in interest on this loan by making 60 monthly payments of $1,275. The amount of money remaining to be paid off on the loan plus interest is given by this function here, where x is the number of monthly payments remaining. So in other words, what we're going to do is find the inverse of this function. So we follow the process, right? Turn f of x into a y. And you have to follow this process every time you do an inverse. Magically switch x and y. And solve for y. Okay, we'll get y by itself. So first we subtract 76,500. Equals negative 1275y. Divide by negative 1275. So x minus 76,500 over negative 1275 equals y. Now remember, we don't leave it as a y. We have to write the proper notation. F inverse of x is x minus 76,500 all over negative 1275. And there we go. Okay? So this reverses it, right? The original function is the amount of money remaining to be paid off in X months. Now with the inverse, it's going to tell us how many months to pay off a certain amount. It switches the input and the output. And that's what they're asking here. Right? How many monthly payments remain if you have 35,700 to pay off? Okay? So in other words, we're going to plug into the inverse. So F inverse of that dollar amount, 35,700. So we plug in 35,700 minus 76,500 all over negative 1275. Punch that into a calculator, and if you punch that into a calculator, make sure you put parentheses around your numerator. You should get an answer of 32 months. Okay, so that means 32 months to pay off $35,000 and $35,700. Okay. Okay. All right, last section here. Additional equations and inequalities. So inequalities are the most fun here, but radical equations. So radicals means square roots, cubed roots, that kind of things, roots. So an equation containing a radical can be converted to an equation that does not contain a radical by raising both sides of the equation to an appropriate power. Okay, so here's the direction. So read those directions, and I'm going to show you how to do some of these problems. Okay, so first step is get a single radical. So in this case, notice we have multiple radicals too, right? One there, one there. Okay, get one radical by itself, which they already did for us. So since it's a square root, we're going to square both sides. Now notice how I did this. Be careful. Look where I put my parentheses. We have to square the entire both sides, not just each individual piece. Okay. So a square root squared, those two things undo each other, right? So we get 2x minus 5 equals. So now what we have to do here is FOIL. Okay, so this is one term, this is the other term. Okay, FOIL, first, outside, inside, last. So first times first, 1 times 1 is 1, plus outsides, radical x minus 3, plus insides, radical x minus 3, plus, and I'm going to write it like this just to show you what's happening, radical x minus 3 squared, because that's the last term times the last term, right? Well, again, we just said a minute ago, when we square a square root, the square root and the square go away. Okay, so we get 2x minus 5. We get 1 plus, now notice we have like terms here. We have two of the same thing, right? So we can add them together. So we'll have 2 radical x minus 3's plus x minus 3. Okay? All right. So we have a radical again, so we need to follow the process again. We're going to get the radical by itself and then square both sides and see what happens. Okay? So we're going to get rid of all this extra stuff. So let's see, 1 minus 3 is negative 2, right? So we're going to add 2 to both sides. So 2x minus 5 plus 2. That gets rid of these. We got to get rid of this x, so we're going to subtract x from both sides, right? So x minus x is 0. So equals 2 radical x minus 3. All right, let's combine some like terms on the left side here. Right, so we've got 2x minus x, which is x. And negative 5 plus 2 is negative 3. Okay, 2 radical x minus 3. Divide both sides by 2. So we get x minus 3 over 2 equals the square root of x minus 3. All right, so we got the radical by itself here. So we'll square both sides. Now be careful. Notice how I write my parentheses again. So a square root squared, they undo each other. So all we're left with is x minus 3 here. Okay. But on the left side, we're squaring the numerator and squaring the denominator. Okay, that's an important rule. In other words, x minus 3 squared over 2 squared. Okay? All right, so x minus 3 squared means FOIL again, right? So x squared minus 3x minus 3x plus 9, right? Because negative 3 times negative 3 is 9. Over 2 squared, which is 4. There we go. All right, we combine like terms. All right, so we get x squared minus 3x, oops, sorry, that'll be minus 6x plus 9. We can multiply both sides by 4, right? If we multiply both sides by 4, we can get rid of those 4, the denominator there. So, and we'll distribute the 4 here. 4x minus 12. We want to get x by itself, so we'll add 12. Okay. We're almost done. I know this one's a lot, but combine like terms. So x squared minus 6x. 9 plus 12 is 21. And we'll divide both sides by 4, right? So 4x over 4 is just an x. Wait, what did I do wrong here? Oh yeah, I'm okay, sorry. Confusing myself here. We're going to subtract 4x because we want a 0 on the other side here. Okay, that's what we're going to do. Subtract 4x. So if we subtract 4x, we get negative 3x squared minus 6x plus 21 equals 0. My mistake there, sorry. Because we want a 0 on the right side. Now notice we can divide both sides by a common factor of negative 3. Each one of these numbers has a common factor of negative 3. So like I said before, make sure you know these are 3 separate things that we're doing here. 3 separate fractions. Okay, that's important. So we'll get x squared plus 2x plus, oops, what happened? There we go. Plus 7 equals 0. Let me make sure I did my math right here. Yeah. Okay. So then we're going to factor, right? So remember, we need to find 2 numbers that multiply to this number and add to this number. Okay? So this one, wait, let's see. I think I made a small mistake here. Let me check my notes. Okay, should be okay. Okay, so then what you would have to do is plug into your quadratic equation and solve. No, I think I made a mistake. Sorry, my apologies. Let me clean this up here. Okay. All right, let me go back to this step. There we go. All right. All right, so we have x squared minus 6x plus 9 over 4. We multiply by 4 on both sides. Okay. So if we I think I had it all right. Anyway, we'll continue this. All right, so all over 2a. All right, so we plug in a, b, and c. And if I did my math correct, you can check it. I may be wrong, but check it. We should get x values of 7 and 3. Okay, and the way you know if you got it correct, you can plug in to the original statement up here before we did all this mess to it, and you should get balance on each side of the equal sign. So I apologize for that mess up there. Okay, here's another problem. Okay, so solve this one right here. So notice this one has a fraction exponent. So when you have a fraction exponent, you're just going to flip that fraction of the exponent and take both sides to that exponent. So first thing we're going to do is get this expression with the fraction exponent by itself. So in other words, we're going to add 4 to both sides. Okay, we're adding 4 to both sides. Now watch what we're going to do. We're going to take this whole left side and take it to the 3 halves power. Again, we're flipping that fraction. And same thing here, 3 halves power. Okay? So notice what happens here. By the rules of exponents, we would multiply these exponents. 2/3 times 3 halves equals 1. An exponent of 1 means you don't even need an exponent, right? Okay? All right, so let's do this, though. So we have 4/3. Well, I'm sorry, 4 to the third, 3 halves power. Okay, so what's going to happen here is we're going to break up 3 halves. So kind of a side note here. So 3 halves is the same as saying 3 times 1/2, correct? Yes. Okay, so let's do that. 1/2 power means square root, right? So what we're going to say is we're going to say 4 to the 1/2 power and take that whole thing to the 3rd power. Okay, watch what we're doing. X minus 6. 1/2 power means square root. Okay, square root of 4 is 2, right? So then we have 2 to the 3rd power. 2 to the 3rd power is 8. So x minus 6 equals 8. We want to find x, so we'll add 6 to both sides. So x equals 14. Okay, and again, you can check that. Make sure you got the right answer by plugging in to the original formula. Okay? All right. All right, now we have solving quadratic inequalities. Okay, so that's a less than, a greater than, less than or equal to, greater than or equal to, etc. Okay. All right, so let's see. So we're going to write an equivalent inequality with 0 on one side with the function f of x on the other side. Solve for f of x equals 0. Create a sign diagram that uses solutions from step 2. So we'll actually do this one in the next, or in 2 examples from now, not this particular example. So let's do this one first. Solving an equation in quadratic form. This is an important method. So this is called substitution, right? So notice this kind of looks like a quadratic, in other words, a parabola, except we have a 4 and a 2 on the exponents here, where normally we have a 2 and no exponent here. Well, not a 0, technically a 1 exponent, right? But we can make it look like that by using a substitution. We're going to say, and you have to write this, let u equal x squared. Okay, so if we're making this substitution, u equals x squared, then x to the 4th equals u squared, right? Okay, if we make that substitution right, just showing you here, u is x squared, so we'd have x squared squared, which is x to the 4th. Okay, do you see that? Okay. All right, and then that means, so we have u is x squared and x to the 4th equals u squared, so we make these substitutions. So x to the 4th becomes u squared minus 5 times x squared equals u, minus 36 equals 0. And we're going to factor. Oops. Okay, we're going to factor. So parentheses equals 0. So we need to find the two numbers that multiply to negative 36, and the same two numbers need to add to negative 5. So we've got a u, a u. We know that 9 and 4 do that, but we have to be careful. We need a negative 9 and a positive 4, right? So remember, practice your factoring methods. Now we have the zero factor property, which means take each individual parentheses and set equal to 0 separately. Okay, so this is u equals 9 and u equals negative 4. Okay, now we did not want to solve for u, we need to solve for x, right? We need to solve for the original variable. Well, we use our substitutions here. So u is x squared, right? Okay, so to solve this, we'll square root both sides. So x equals, now remember when you square root both sides, you have to do the plus and minus thing, right? So we got two answers here, plus and minus 9. Now this one, be careful, right? So we're going to square root both sides, but remember how we said, well, we can't do the square root of a negative number, but then later we talked about imaginary numbers. So remember, so this is side information, remember, I equals the square root of negative 1. Okay? So we'll rewrite that negative square root of 4. So we actually have plus or minus the square root of negative 1 times the square root of 4. Okay, so we'll simplify. So x equals plus or minus. So square root of negative 1 is I, and the square root of 4 is 2. So we'll put the 2 in front of the I. Okay, so there we go. So there's your answers. Okay, so that was substitution. All right. Here's an example with the inequality. So model rocket is projected straight upward from ground level according to this equation here, where h is the height in feet and t is the time in seconds. During what time interval will the height of the rocket exceed 320 feet? So exceed means greater than, right? All right, so h is the height, 320 feet. So we're going to say this function, negative 16t squared plus 192t exceeds, in other words, we want it to be greater than 320 feet. Okay? So the easiest way to solve problems like this is look for a greatest common factor. So we have negative 16, 192, and 320. Luckily, all of those are divisible by negative 16. Right, so whatever we do to one side, we got to do to both sides. So this makes it nice and easy. So that's t squared minus 12t greater than, actually we have to be careful. I'm not going to write that inequality for just a second. This is negative 20. Remember when we multiply or divide by a negative number, when we have inequalities, we need to flip the inequality. So now it's less than instead of a greater than. Okay, so again, whenever you multiply or divide an inequality by a negative number, you flip the inequality. Okay? All right, we need a 0 on one side, so we add 20 to both sides. Okay? We're going to factor right here. So again, get good at factoring, right? We got t. So we need two numbers that multiply to positive 20 but add to negative 12. Okay, and you'll notice if you do a little bit of work, 2 and 10 do that, but if they're both negative, right? Negative 2 minus 10 is negative 12. Negative 2 times negative 10 is positive 20. Okay, so the way we do this, right, we take a number line. Oh, I'm sorry. We need to solve first. So we take t minus 2 equals 0, t minus 10 equals 0, and solve. So t equals 2, t equals 10. Now we take a number line and we write those two numbers on there. There's 2, there's 10. So what this does is it sets up three intervals of x values, right? So anything less than 2, more than 10, and between 2 and 10. Now we need to test those 3 intervals. And it's easiest to test with the factored version here, this inequality. So pick any number in this interval, anything less than 2. Pick an easy number, 0, right? If we plug a 0 in for t, right, then we get -2 times -10. -2 times -10 is positive 20, right? So we ask ourselves, is 20 less than 0? It is not, right? Okay? All right. So what that tells us is this interval does not work. Okay? Now we pick another a number in between 2 and 10. Pick easy numbers, like 5. Okay? Let's plug a 5 in, again, to this factored version here. So 5 minus 2 is 3. 5 minus 10 is -5, which is -15, right? Is that less than 0? Yes, it is, right? So we'll put a plus sign here for this interval because it works. Now the nice thing is you pick any number in these intervals and test it, then it makes it true for the whole interval. All right, so now we pick something bigger than 10. Pick anything, I don't know, pick 20, right? 20 minus 2 is positive 18. 20 minus 10 is positive 10. This is 180, which is not less than 0, so this interval does not work. So to answer the question up there, the time interval, so we can write it in inequalities, it's from 2 to 10. That's the only interval that works, not including those 2 and 10, the 2 and 10. In other words, from 2 seconds to 10 seconds. That's the answer. Okay? All right, practice problems like that. You definitely see that kind of stuff again. All right, and we have power inequalities, right? So to solve a power inequality, first solve the related equation, then use graphical methods. So we're not going to really talk too much about that, but we are going to talk about inequalities involving absolute values. Okay, so for absolute values, you're familiar with this. These are just different ways to write absolute values. So this is the most common one you'll see, the absolute value of u less than a. Just means that u is between negative a and a. Okay, and you can see the other three are very similar to that. So this is what we're going to do. So we're going to solve the inequality and verify the solution graphically. Okay, so what we're going to do is we're going to rewrite this using these methods up here. Now notice we have a less than or equal to, so we'll use this one right here. Okay, so in other words, we're going to say that -8 less than or equal to 2x minus 2, and notice I dropped the absolute value, right? It tells us to drop the absolute value, less than or equal to positive 8. Okay, we're just using that definition above. So now what we think about here is basically like a three-piece equality or inequality in this case. We're going to follow basic algebra rules. Whatever we do to one side, we do to all sides, but in this case, we've got 3 things we need to do it to. In other words, watch. We want to get x by itself in the middle. That's our goal. Okay? So first step is we need to add 2, which means we have to add 2 here and add 2 here. Okay, notice we're doing it to all 3 parts. Okay, so -8 plus 2 is -6. These go away, so we get a 2x, and 8 plus 2 is 10. Okay, so again, we want x by itself in the middle. So we'll divide by 2. Again, divide everything by 2. So that's -3 less than or equal to x, right? Because 2 over 2 reduces away, less than or equal to 5. Okay? In other words, our values go between -3 and +5. And if you notice on the graph, there's -3 and there's 5. Okay? So graphically verifies our algebra. Okay, that's chapter 4 for you. Thank you very much.